we're going to talk about the sum and the difference of perfect squares and cubes. So this first page is simply dedicated to talking about what is a perfect square, and then we'll talk about what is a perfect cube. We have a simple definition for a perfect square, and it turns out it's just simply the square of another integer. So any number that can be written as the square of an integer, we have a perfect square. And that's a perfect square as far as a number goes. So for instance, in example 1, we have 9. Well, 9 can be written as 3 squared. Okay. However, 8 is not a perfect square because we cannot write an integer and square it and get an 8. Okay. So we're only squaring integers, and that gives you a way to sort of become familiar with some of the perfect squares right away. So if we take 1 and square it, we get a 1. So by definition, 1 is a perfect square. 2 squared gives us a 4. And so 4 is a perfect square. 3 squared is 9. 4 squared equals 16. 5 squared is a 25. And we could keep going and going. But you notice that we skipped numbers in between each successive perfect square. So no perfect squares between 1 and 4, no perfect squares between 4 and 9, and so on. These are the only perfect square integers. Alright, so that's how you identify numbers that are perfect squares. Uh, you, instead of writing out a list, if it was a large number, what you could do, for instance, if you were to want to know, um, is 144 a perfect square, then you could simply go to your calculator, hit the square root button, put a 144 inside of the radical symbol, and your calculator would give you a 12, and 12 is an integer, so 144 is a perfect square. If you get back a number with digits beyond the decimal point, then it's not an integer, and so you wouldn't have a perfect square. So for instance, if we took the square root of 140, okay, you would not get an integer in your calculator. Okay, so real simple to identify perfect squares number wise. What about when you're dealing with an integer, or I'm sorry, a variable? Well, here we can say x to the 8th power is a perfect square because x to the 8th can be written as a x to the 4th power squared. Okay, if we apply the power rule, it says that if we have a variable with an exponent that's raised to an additional exponent, then we can simply multiply these two exponents together. Doing so, 2 times 4 would just simply give us the 8 back. Okay. However, x to the 9th, if we were to try the same trick, square the variable x with some exponent here, that exponent would have to be a 4.5. Okay, and we only want whole number exponents here. We don't want an exponent such as 9. It's not a perfect square because 9 is not evenly divisible by 2. Okay, so x to the 9th power is not a perfect square variable. Okay, so real quick, example 3, whenever you're asked for the square root of a particular number or a variable term, square root, the symbol is this, Okay, it's called a radical. And it simply asks the question, what do we square raised to the power of 2 to get whatever is listed underneath the radical? So to get that particular number. Alright, so what do we square to get an x to the 12th power? What do we square? So this is the question. We don't know what that is. What do we square to get x to the 12th? Well, variables are the easy ones. All we have to do is simply take the exponent 12, divide it by 2, and we get a 6. 2 goes into 12 evenly. So we could just simply write an x to the 6 inside the parentheses. So to answer the question, x to the 6 is the square root of x to the 12th. It's what we raise to the second power. What is the square root of a plus b to the 4th in example 4? Well, if we take a plus b squared and then we square that and apply the power rule, we get a plus b to the 2 times 2. Okay, power rule says we multiply these exponents, and that would give us a plus b to the 4th power. So the square root of a plus b to the 4th is a plus b squared. In example 5, we're given a term, and there are several variables, and we have a coefficient. So to get the square root of this term as a whole, we only have to take the square root of each individual part. So first we say, what is the square root of 9? Well, that's 3, because 3 squared equals 9. What is the square root of a squared? Well, that's just simply a. We take the 2 and divide it by 2. Okay. What's the square root of b to the 8th? We simply take b to the 8th and divide the 8 by 2, and so we get a b to the 4th. So maybe I should write the same thing down here for this a squared. What we did is we simply took 2 divided by 2 for a square, and we got a to the 1st power, or you could just simply write an a. The one's understood. And then finally, the last part of the term is a c to the 6. We take the 6 and divide by 2, and we get a c to the 3rd. So what is the square root? Well, we just simply piece together all of these square roots of the different parts of the term, and we have it. It would be 3a, b to the 4th, c to the 3rd. So that brings us to what we're really interested in, taking a polynomial of a particular kind and figuring out a way to write it as the product. Okay, so you can see that we have subtraction between two terms here. So we have the difference, okay, and then you'll also notice that x squared is a perfect square, where the square root is an x. And then likewise, 9 itself is a perfect square because the square root of 9 is a 3. So this is subtract, the difference of two perfect squares. Alright, off to the side, what we have here is a template as to how we write out the factors. Okay, And so what we have is we've taken the first square root and we've placed it at the first of each factor. Okay, it becomes the first term of each factor. So we put an x here and then an x there. Now for the second square root, we just simply use it as the second term of each factor. And then you'll notice that the difference of squares factors as the sum plus and the difference of the two square roots. So it doesn't matter which one comes first, we simply put a plus and then a minus between the two square roots. And it's that simple. Okay, I guess the work required for factoring these types of polynomials is just figuring out the square roots of each of the terms. So example 6, we see that we have an x squared and a 49. So we say, what is the square root of an x squared? We just simply divide the exponent by 2 and we get an x to the 1, or just an x. And then the square root of 49, if you put that in your calculator, you see that 7 times 7 is a 49, so the square root is 7. And we're also, you want to check that we are dealing with the difference of two perfect squares. Now all we have to do is piece together our two factors, and the difference of squares always factors as a binomial times a binomial. Okay, two terms in each factor. We already know what those terms are going to be. The first term is just going to be the x, the first square root. So we put an x in each spot. The second term of each binomial is going to be the second square root. So we put 7 and 7 there, and then we just simply give the two 7s opposite signs. So we have the difference and the sum. And that completes example 6. So example 7, we check each term, make sure they're perfect squares, and so here we have a 49 and an a squared. To check the variables, you just simply make sure that each exponent is divisible by 2. So here, if we took a 7 and an a and squared it, then we would get back a 49a squared. So this first term is a perfect square, and the square root is the 7a. The square root equals 7a. Okay, 100 is a 10 squared. Okay, 10 squared equals 100. So the square root equals 10. And we're also looking at the difference between these two terms. So it is the difference of perfect squares. We go off to the right, and we put two parentheses to the right. These sets of parentheses are multiplied by one another, and each one of these has two terms. They're both binomials. The first term of each one is the 7a that we found. The second term is the 10, and then we just simply put a plus and a minus between one and then the other. So we don't want these signs to be the same. We just want these signs to be the difference, or to be different. And we're finished. That completes example 7. Example 8, there's an extra step that we need to complete before we can use this new way of um, factoring the difference of squares. You do not want to forget about the ways that we've already talked about in regards to factoring, that being greatest common factor and factor by grouping. So the first thing that you would want to pick up on here is that each of these terms has a common factor. They both have an m, and the coefficients are both divisible by 2. Both have an m, and both divisible by 2. So they have a greatest common factor. So we want to take out that greatest common factor first. So we simply write it down, 2m, and we go back and we divide this 2m from each of the two terms like we did in the previous chapter. So I write 2mn squared divided by 2m, and then minus 8m divided by 2m. So we're simply putting the remainder inside the parentheses, and we rewrite this. We cancel out the 2m. 8 divided by 2 is a 4. And so inside our parentheses we're going to have an n squared and a minus 4. And here's the point where you should recognize that we are dealing, at least part of this polynomial is the difference of squares, because n is a perfect square and the square root is n, and then 2 squared equals 4. So the square root equals 2. And we have the difference. They're subtracted. So we want to factor this completely. You simply just bring down the 2m. You don't want to throw it away. And we're going to break up this second part into the two binomials. We place an n as the first term in each, a 2 as the second term, and then we place a plus and a minus between the two. And at this point we've factored this polynomial completely. Finished. Now you may be wondering about what if we were to put a plus sign between the two perfect squares. Well, we already know that if we try to factor it with a minus and a plus between the two, then we're simply going to get z squared minus 16, which doesn't match the polynomial that we're trying to actually factor here. We want a plus in between the two perfect squares. So minus plus or plus minus isn't going to work. That only leaves two possibilities that we have written here in example 9 and 10. We have a plus plus and a minus minus combination. So are these two ways a legitimate way to factor z squared plus 16? Well, to check it, we simply just FOIL the two binomials, and doing so we get a z squared plus a 4z. Okay, that takes care of the top two arrows, and now the bottom two we have a 4z, and then a 4 times 4 would give us a 16. And so we do have the z squared and we have the plus 16, but we have these two middle terms that give us an extra term that wasn't in the original polynomial. There is no 8z over here in between the z squared and the 16. So this is not a way to factor the sum of squares. If we try the other way with minus signs, then we simply come out with a z squared minus an 8z plus a 16. And again, we have this extra factor, or extra term, I should say, that wasn't present in the original polynomial that we were trying to factor. So this way does not work either. Now you can try to come up with a way to factor this, but any way that you factor this or break it up into two or more factors, those factors are not going to be polynomials. Okay, so what we say about z squared, the sum of two perfects squared, z squared plus 16, is that it is a prime polynomial. You can't take two polynomials or three or more, multiply them together, and get a z squared plus 16. So here you notice that it's the first one, example 11. The first one out of the gate is this is a perfect square. The square root's x, and then the square root of 49 is 7. But we're talking about the sum of two perfect squares, so this is prime. Now one thing that I want to point out is that if I were to take this polynomial and change it and say, for instance, we were given the polynomial 2x squared plus 98. Okay, you can factor this with the greatest common factor. So if we were to take out a 2, then we would be able to factor this polynomial. But after we took out the 2, the x squared plus 49, this part would be prime. So just because it contains, the polynomial contains one of these, we don't say the polynomial, the original one as a whole, is prime. This one is not prime. We can take out a 2. But this one that doesn't have a greatest common factor, the x squared plus 49, is prime. Okay. So that brings us to example 12, and what we have here is an x to the fourth, and 4 is divisible by 2 evenly. Okay, 4 divided by 2 is 2. So we get an x squared is our square root. So x squared squared equals an x to the fourth. So our square root of this x to the fourth equals the x squared. 16, it's real simple. 4 squared equals a 16. So our square root equals a 4. So we're going to break it up into two factors. We write x squared in the first parts of each. First term of each factor, and then the second term is a 4, and one becomes a plus, the other one a minus. Now you need to recognize that you have not factored this polynomial completely. This factor however is not factorable. It is the sum of two perfect squares, but you should pick up on the fact that this is the difference of squares, so we can factor this further. Factor further. So this one, the difference of squares, so we're going to break that one up into these two factors, And then this one is prime, so we're just simply going to bring it down to the next line and write it out to the side. We want to keep up with all of our factors that we find along the way. Now, if we divide this 2 by a 2, we get a 1. So the first factor, or the first term of each of these, would be an x. And then the square root of the 4 is a 2. So we place 2's as the second term of each factor. We put a plus and a minus between one and the other. And so now we're finished. We have factored the original polynomial completely. Okay, example 13. Notice that each term has an x. Each term has an x. Both are divisible by 2. And that's it. Okay. Now, they both have an x, but we pick out, for the greatest common factor, because that's where we're going with this, we pick out the x with the smallest exponent. And in this case, they both have a 3, so our greatest common factor is going to have an x to the third in it. And this is a 2, so the most that we can divide out is a 2. So our first step for factoring this polynomial is to write 2x cubed out. We go back and divide that out of each of the two terms. So a 162 divided by 2 would give us an 81. If we divide out the x cubed, then they just simply cancel out. And then we have a minus between the two terms. If we divide out the 2 and the x cubed from the second term, we're left with a v to the fourth power. Alright. Now, we're not finished factoring this polynomial, because by this point you should recognize this second factor as a difference of squares. So we break it up into two binomials. 81 is the square of 9. 9 squared equals 81. So 9 is going to be our first term. We place a plus and a minus after each 9. And then the square root of v to the fourth is a v squared. I just simply took the 4 and divided by 2. Now, 9 is a perfect square and v squared is a perfect square, but this term, or this factor, is the sum. So it's prime. We can't factor this any further. However, this part is the difference of a 9 and a v squared, which are both perfect squares. So we can factor it again. So in the end, to factor this completely, we end up with 4 different polynomials as factors. A 2x cubed, a 9 plus v squared, a 3 minus v, and a 3 plus v. So up until this point, we've talked about the difference of squares. Now we're going to shift gears and talk about the sum and the difference of cubes. So we're sort of going to follow the same logic as we did with the squares. Number-wise, what is a perfect cube? Well, in terms of integers, we just simply take the first few integers, 1, 2, 3, 4, and 5, and we could also have the negative versions of these, and we cube them. 1 cubed is a 1. So 1 is a perfect cube. 2 cubed is an 8. 3 cubed is a 27. 4 cubed is a 64. 5 cubed is a 125. And I would recommend that maybe you go a little bit further out past 5 and just get familiar with some of these perfect cubes. Now, since any of these could have a minus sign, okay, a -5, -4, -3, and so on, then the negatives of these numbers are also perfect cubes. Alright, so why is 8 a cube and 9 is not? Well, 8 equals a 2 cubed. But 9, on the other hand, if you cube something to get a 9, then this is not, whatever this number is not an integer. Okay, we skipped it on the list. We went from 8 to 27, so any number in between 8 and 27 is not a perfect cube. Now for 15, just like the squares, the variables are the easiest ones because we simply have to look at the exponents of the variables and ask ourselves whether they're divisible by 3. So x to the 9th is a perfect cube because x to the 3rd power cubed gives us an x to the 9th. 9 is divisible by 3. Y to the 8 is not. Of course, the question said so. Y, 8 is not, I guess we should say, evenly divisible by 3. Okay. So now we know what a perfect cube is. 16 is sort of a special question. It says, can we find a term that's both a square and a cube? Well, for it to be a square, it has to be divisible by 2. For it to be a cube, it has to be divisible by 3. So, can we find an exponent that's divisible by 2 and 3? Well, the answer is yes. One such number would be a 6. So if we wrote x to the 6, this would be both a perfect square and a cube. So on one hand, we could write it as x to the 3rd power squared, and on the other hand, we could write it as an x to the 2nd power cubed. Now, example 17, all we have to do is take the cube root of each of the individual parts. 125, x cubed, y to the 6th, z to the 15th. Okay, so the cube root of 125 is 5. The cube root of x to the 3rd is x. So y, because 5 cubed equals 125. As for the x cubed, well, x cubed equals the x cubed. Okay, 3 is divisible by 3. What is the cube root of y to the 6th? Well, it's y to the 3rd. 6 divided by 3, or sorry, let me back up a second. This should be a 2. The cube root of y to the 6th is y squared, because 6 divided by 3 equals 2. So for z to the 15th, the cube root is z to the 5th power, because 15 divided by 3 equals 5. Alright, so the cube root equals 5. X y squared and z to the 5th. Okay, so now that we know what a perfect cube is, we're going to talk about these polynomials in particular that we're going to factor, the sum and the difference of two cubes. So you can see here that we have an x to the 3rd and a y to the 3rd, and this first term and this second term are perfect cubes because 3 and 3 are both divisible by 3, of course. So here we have the difference because of subtraction, and here we have the sum, the plus, and off to the side we have our factors that we can break this up into. Okay, so you have to pretty much memorize these templates in order to be able to factor these types of polynomials. Okay, and what you want to notice is that we factor these polynomials as a binomial, the first factor, and then the second factor is the trinomial. Okay, we have 1, 2, 3 terms in both of these second factors. So the sum and difference of two cubes factors as a binomial and a trinomial. 2 terms and then 1, 2, 3 terms. So if you really look closely at these two ways to factor, you'll notice a pattern. Which we talk about right here. Okay, and specifically we're talking about the trinomial factor, the second factor, this one. Alright, so the first term of this trinomial, if you look, in each case is an x squared. Well, what is the x squared? Well, it's simply the first cube root. Okay, if you take this first term in the polynomial that we're trying to factor and you take the cube root, okay, cube root, you get an x. Okay, and then if you square that x, then you get the first term of the trinomial. Okay, so the first term of the trinomial is the square of the first cube root, or the cube root of the first term here, the x cubed. Okay, now if we go back and look at the second term, then what we see is that it is simply the product of both of these terms in this binomial, the first factor. Okay, so we say that it is the product of the cube roots. Okay, and just like the x cubed, here we have the y cubed, and if we take the cube root, we see that we have a y as our second term of the binomial. Okay, so the third term of the trinomial is a y squared. How did we get the y squared? We simply took this y and we squared it. Okay, and this y is the first cube, or sorry, the second cube root. Okay, second cube root y. So square of the second cube root. Alright, and you have that written out down here as well. So looking at these two figures at the bottom of the page, another thing that you want to point out are the signs. Okay, notice that all of these terms are the same, x and x, 4 and 4, okay, x squared and x squared, 4x and 4x, 16 and 16. So regardless of whether you have the sum or the difference, we're going to have the same components here. But now you notice that there is a difference between the signs in some cases. The third sign being the same in both. So what we do in order to remember the signs is we say that the first sign that we run into in our factors is the same, okay, is the sign of the polynomial that we're factoring. Okay, this is the sum, so this first sign is a plus. Now the second sign is going to be different, and then the third sign is well, it's always a plus, so maybe I shouldn't draw an arrow up here. So I'll say always plus, always plus. Okay, and so you see down here for the difference of cubes, we have the same sign for the first sign, and then we have the different sign for the second sign, and the third sign is always a plus. Okay, so you have to see the pattern in the templates that we're given. Alright, here we are, the last page of the chapter. What we want to do is pick out our cube roots. Cube roots. Well, cube root of this variable term is just simply the 3 divided by 3, so we get an x. 3 divided by 3 is 1. The cube root of 8 is a 2. So we have all the parts to construct our two factors, which is going to be a binomial and a trinomial. So we're going to have 1, 2 terms in the first factor, 1, 2, 3 in the second one. We place an x and a 2 here. These two parts make the binomial, these two cube roots, and the sign that we put between them is the sign that we have between the two perfect cubes, so minus. And then for these two, the first and the last term of the trinomial, we simply square the two parts, or square the two cube roots. The middle term of the trinomial is the product of the two cube roots. The third sign is different from the first one. These two signs are always different, and the last sign is always a plus. Alright, the only thing that you want to go back and do with this would be to simplify this trinomial in the sense that you want to go ahead and square this 2 and write it as a 4 instead of leaving it written as a 2 squared. So example 19, we see that we have plus, so it's the sum. This 3 is divisible by 3, of course, so it is a cube root, or a perfect cube. Cube root's x. 27 is a perfect cube, and the cube root is 3. So these are the parts that we need to construct our 2 factors. We write x3, x squared, 3 squared, and then we multiply the 2 together. The first sign is the same, plus. Second sign is different, and the third sign is always a plus. And so now we simply just go back and work out these squares. Here we just had an x squared, there was no number to square. For the last term, we want to write it as a 9, and we're finished. 20, we have the cube root is a 2 and an x, and then 27 again, cube root is 3. So we write 2x and a 3. The sign was the difference of perfect cubes, so we put the difference between these 2 parts, the 2 terms, minus. Then we have a trinomial. For the first term, we square the 2x. For the third term, we square the 3. And then for the middle term, we multiply the 2 together. And then we fix our signs. The second sign is different than the first one, and the third sign is always a plus. And now we just go back and square our numbers for our trinomial, and we get a 4x squared, a 6x, and a 9. Our last 3 of the chapter. Here we have the difference of perfect cubes, and I know it's a cube because both exponents are divisible by 3, and 125 and 64 are cubes because I'm just familiar with the numbers. Okay, the cube root of 125 is 5. 3 divided by 3 is 1, so we have a z to the first power. 64 is a 4 cubed, and t to the third, we have a t as the cube root. So these are the parts that we use to construct our factors. 5z, 4t. This has a minus between the 2 perfect cubes, so we put a minus between these first 2 terms. Off to the side, we write out our trinomial. Okay, 1, 2, 3 terms. The first term is the 5z squared, and we want to put this in parentheses just to indicate that we're squaring both the 5 and the z. The last term is the 4t squared, and the middle is the product of the 5z and the 4t. The signs are, first 2 signs are different, and then the last sign is always a plus. We go back, we clean up our trinomial, we apply these exponents. 5 squared is a 25, z squared is a z squared, 5 times 4 is a 20, 4 squared is a 16, and there we have it, our binomial factor and our trinomial. Now this one requires a first step before we go into trying to factor it as a sum or difference of cubes. Again, you always want to keep in mind greatest common factor and factor by grouping, but we don't have four terms here, so factor by grouping is out. You need to pick up that the greatest common factor of these two terms is a 2. 54 is divisible by 2, and 2 is definitely divisible by 2. So that's what we need to do first. So we factor out the 2. We put what's left in the parentheses, which would be a 27 and an m cubed. And here we just see a simple, straightforward sum of cubes. So this is going to break up into a binomial, 2 terms, and a trinomial, 3 terms. 3m, 3 squared, m squared, and then in the middle a 3m. This started with a plus, so the binomial has a plus. This sign is different, and the third sign is always a plus. And here we can just simply go back and turn the 3 squared into a 9. So as a final answer, you want the binomial and you want the trinomial, and I'm sure you'll have that, but you also want to keep up with this 2 for every line that you use to work out this polynomial, to factor it. Okay, so our last one, example 23. You see that they both have a b, and 81 and 24 are both divisible by 3. So we say greatest common factor equals 3b, and then they both have an exponent of 2 for the b, so b squared is part of our greatest common factor. We're not worried about a trinomial or binomial or a difference of cubes or anything like that. At this point, we're just simply putting the remainder inside the parentheses. So 24 divided by 3 is 8. B squared divided by b squared, well, the b squared just cancels, and we're left with this c to the third. There was no c a part of our greatest common factor. 81 divided by 3 would give us a 27, and b squared divided by this b squared just simply cancels out, and we have a minus in between the two. So we're just simply focused on putting the remainder inside these parentheses. At this point, you want to recognize that these parentheses contain the difference of cubes. The first cube root is a 2c. The second cube root is a 3. We started with a minus, so a minus goes between the 2c and the 3. And now we square the 2c for the first term, square the 3 for the last term of the trinomial, and then we multiply the 2 terms together, the 2c and the 3, and we fix our signs. First 2 signs are different, the last sign's always a plus. Square the 2, we get a 4c squared. 2 times 3 is a 6c, and 3 squared is a 9. And so we're finished, and that completes chapter 4. Thanks for watching.